Well, thank you very much for the invitation. Yeah, I will talk on Viterbo's conjecture for Lagrangian products in R4. And let me briefly start with a short outline. So first, I will start with the motivation why studying Viterbo's conjecture is important. Then I will show you some main results. And then, if time allows, I will show you some proof ideas. So let me briefly start with the motivation. And I will directly start with a certain version of Viterbo's conjecture, namely the one for the EHZ-capacity of convex sets, which says that if we look at the volume of a convex set in R to the n, at R to the 2n, then this is always greater or equal than the EHZ-capacity of this convex set to the n divided by n factorial. Where for the following, I will just use the following as a definition that the EHZ-capacity of a convex set is the minimal action of all closed characteristics on the boundary of the convex set. And a closed characteristic, I mean an absolutely continuous loop on the boundary, which satisfies this differential inclusion that the velocity in every point is an element of the J rotated normal cone, where J is a symplectic matrix. So, and when you know, look below, if we introduce a systolic ratio, then one can reformulate Viterbo's conjecture as a systolic inequality, which says that the Euclidean ball is the convex set which maximizes the systolic ratio. And part of this conjecture is that every other maximizer of the systolic ratio is symplectomorphic to the Euclidean ball. In other words, one can say that that Viterbo's conjecture says that among the convex sets of fixed volume, the symplectic capacity is maximized for the Euclidean ball, and every other maximizer is symplectomorphic to the ball. Okay, let me now show you some related conjectures in order to motivate the study of this conjecture. So first of all, we have this conjecture that all symplectic capacities coincide on the class of convex sets in R to the 2n. And this conjecture would immediately imply that Viterbo's conjecture for the EHZ-capacity is true, because one can easily show that Viterbo's conjecture is true for the Gromov width defined here, and then one is done. Further, this conjecture concerning the coincidence of symplectic capacities would imply that if we look at the equality cases, then they are also always symplectomorphic to Euclidean ball. Because otherwise, if we would have an equality case which is not symplectomorphic to Euclidean ball, then the Gromov width of this equality case would be less than the EHZ-capacity of this equality case, and then this would be a contradiction to the coincidence of capacities. So another related conjecture is the Mahler conjecture from convex geometry from 1939, which says that the Mahler volume, which is the volume product of K and K polar, is always greater or equal than 4 to the n divided by n factorial, and this is for centrally symmetric convex bodies. And one can say that Mahler's conjecture, in a certain sense, captures the roundness of centrally symmetric convex bodies, where Blaschke and Santallo proved that the Mahler volume is maximized for the ellipsoids. And the Mahler conjecture says that the conjectural minimizers of the Mahler volume are cubes and cross polytopes. And so the pointiest, one can say the pointiest centrally symmetric convex bodies. And a nice fact now is that Viterbo's conjecture implies Mahler's conjecture, because Abstein, Avidan, Karasev, and Ostrova proved that if one looks at the EHZ-capacity of these Lagrangian products K cross K polar, then this is always equal to 4. And then one sees that exactly the same factor appears depending on n, and one has that Viterbo's conjecture implies Mahler's conjecture. And also besides this, from a conceptual point of view, it is interesting to look at Mahler's conjecture from the symplectic point of view, because the difficulty of Mahler's conjecture is that there are many, so there are different conjectural minimizers, so cubes and cross polytopes, and it's really difficult to conceive of any minimization process or sort of flow which is converging exactly to these minimizers and to no others. And if we now look at Mahler's conjecture from the symplectic point of view, the conjectural minimizers of the Mahler volume translates into the conjectural maximizers of the systolic ratio. And the conjectural maximizers of the systolic ratio are just the Euclidean ball and the images under symplectomorphisms. So this is interesting to look at Mahler's conjecture from this symplectic point of view, especially from the perspective of Viterbo's conjecture. Okay, then one can say that the study of, or this implication motivated to study Viterbo's conjecture for the Euclidean capacity of these Lagrangian products in general. And for this, for these configurations, one has a nice result that one can express the action minimizing closed characteristics on the boundary of these Lagrangian products K cross T, where we can interpret them as length minimizing billiard trajectories. And these are Minkowski billiard trajectories, and these are just billiard trajectories in K, where the bouncing rule is determined by the geometry of T, and one can derive these system depending on the bouncing points, and then one can construct the billiard trajectories easily. So for example, if we have here a vector in the normal cone, this vector gives me the direction of the dual billiard trajectory over here, and this vector over here gives me this direction, and so on and so on. So yeah, based on this characterization, this Minkowski billiard characterization of the Euclidean capacity of these Lagrangian products, one immediately gets that Viterbo's conjecture also can be expressed as a systolic Minkowski billiard inequality, where one tries to bound the minimal length of Minkowski billiard trajectories in terms of the volume of the billiard table. Okay, based on these related conjectures, now one can ask the following 4 questions, which will be of importance for the following. So the first question is it possible to prove Viterbo's conjecture for certain Lagrangian products? Second question, what are the equality cases of Viterbo's conjecture, or is it possible to classify them? And the third question would be, if one has equality cases, are they symplectomorphic to Euclidean balls? And the fourth question would be, is it possible to characterize the equality cases in a certain sense? And this will lead us to the Zoll property. So let me start with the answers of these questions in the part of the main results. So the first answer, so the answer to the first question is the following theorem, which says that if we look at any trapezoid in R2, so now we are in 4 dimensions, so any trapezoid in R2 and any convex body in R2, T, then the Lagrangian product Q cross T satisfies Viterbo's conjecture. And here I mean by trapezoids the usual definition. So we have quadrilaterals where one has at least 2 sides parallel. And I also include triangles as degenerated trapezoids. And then one can say that this result is an extension of a result by Alexei Balitsky some years ago, who proved that Viterbo's conjecture is true for these triangle and parallelogram configurations, and this theorem can now be seen as a generalization to the trapezoid configuration. And an immediate consequence would be, yeah, that one can solve some of the systolic Minkowski billiard inequalities, namely the one where the unit balls are trapezoids. Okay, then concerning the answer to the second question, so whether it is possible to determine equality cases. So now I split this again into these 3 configurations: triangle configuration, parallelogram configuration, and here the trapezoid configuration, where I mean, yeah, here strict trapezoids. I mean by this trapezoids which are neither parallelograms nor triangles. And if we are now in the triangle configuration and start with any triangle on the left side, I call this delta. And if we then rotate this delta by 90 degrees to the right and 90 degrees to the left, then one gets the red and the blue triangle. And if one now looks at the volume minimizing convex hulls of these 2 triangles, then one can get hexagons and parallelograms. And all of these volume minimizing convex hulls are T's for which delta cross T is an equality case of Viterbo's conjecture. What exactly this means, I will say in a few moments. So then, first of all, concerning the parallelogram configuration. So if we start with any standard square on the left, and we choose any diamond on the right where A1 and A2 are arbitrarily chosen between 0 and 1, then all of these configurations are equality cases of Viterbo's conjecture. And then for the trapezoids, which are neither parallelograms nor triangles, one can find for any trapezoid a parallelogram P such that Q cross P is an equality case. But this case is already included within the second, where the trapezoid appears on the right side, and then one has to choose the associated parallelogram on the left side. So it's just by reflecting. So then the third question was, which of these equality cases are now symplectomorphic to a ball? And yeah, now one can say that all of them are symplectomorphic to a ball, except for the one where we have here, so equality cases where when we have here hexagons and parallelograms, and one can prove that these are symplectomorphic to the ball if one has here parallelograms. So this immediately implies that an open question whether these Lagrangian products of a triangle and a hexagon, which are convex volume minimizing convex hulls of these two rotated deltas, whether these are Euclidean balls through symplectic classes. So what does it mean in detail? So let us look at these two triangles again, the blue and the red. And if we place the red triangle such that it touches this bigger triangle, then we always get a parallelogram as volume minimizing convex hull. And if we place the red triangle in the interior of this bigger triangle over here, then one gets a hexagon. And for all of these positions of this red triangle within this bigger triangle, one has an equality case of Viterbo's conjecture and symplectomorphicity only if the red triangle touches the boundary. So I have to say here that recently Ostrova, Ramos, and Sepe announced that they are able to prove that the Lagrangian product of an equilateral triangle and a regular hexagon are in fact Euclidean balls, and this would mean that, so this is not published so far, but if this is true, then this would mean that all equality cases known for this Lagrangian setting are symplectomorphic to a ball. Okay. Then the answer concerning the fourth question, whether it is possible to characterize the equality cases in a certain sense. So first of all, we have to remind ourselves that all the equality cases presented before were polytopes. So we have facets and lower dimensional faces. And if we now look at the characteristics on the boundary of these equality cases, which run over the interiors of the facets or of the top dimensional faces almost everywhere, then they satisfy the properties that they are always closed. They run over exactly 8 facets, and they minimize the action. And one can say that the union of these characteristics stands on the boundary of these equality cases. And this is sometimes called the Zoll property for smooth cases. And here we have this this polytopes, and one could have expected that for characteristics which are moving on lower dimensional faces, this is not true. And here are two counterexamples for this, that if we look at characteristics on lower dimensional faces, then one can find closed ones which are not minimizing the action. Here one within the triangle configuration, and here also one within the parallelogram configuration. Okay, now the last 5 minutes, let me say something concerning the proof ideas. So first of all, concerning the proof of the answer to the first 2 questions. So I already said that Viterbo's conjecture can be written as a systolic Minkowski billiard inequality, where one tries to find the length, or one tries to bound the length minimizing billiard trajectories by the volume of the billiard table. And now it is possible to rewrite this problem as a covering problem, which says the following, that one tries to find the volume minimizing convex covers of any closed curve with a fixed length. So here the fixed length is depending on the geometry of T, and if one chooses here square root of n factorial, then one gets here the conjecture that this is greater or equal than 1. And this is now the covering problem, which is equivalent to Viterbo's conjecture for these Lagrangian products. And now the idea is, first of all, I can say that these covering problems, or this covering problem, is related in some sense to famous problems in geometry. For example, Moser's worm problem from 1966, Wetzel's problem from 1973, or Bellman's lost in the forest problem from 1955. And perhaps later in the discussion, I can say something concerning this relation. But the idea now is to start with this covering problem and to solve this for the configurations presented before. And this is exactly what one can do. So for the triangle, for the parallelogram and trapezoid configuration, here one can solve these covering problems. And here I've shown you some of the length minimizing billiard trajectories. And an aspect which has to be noticed is that these sets on the right are characterized by being volume minimizing convex hulls of a finite number of closed curves of a certain length. Here we have two triangles. Here we have two line segments, and here we have two triangles and one line segment. And so this is, one can say the idea to reduce these covering problems to a finite number of closed curves, which has to be covered, and then one can prove that this is true. So this conjecture concerning covering problem is true for these configurations. Okay, then the answer concerning the proof concerning the answer to question 3. So which of these equality cases can be proven to be symplectomorphic to a ball? This result relies on an embedding result by Felix Schlenk, which says that if we have here a diamond when A1 and A2 are between 0 and 1 and a square, then the Lagrangian product is symplectomorphic to a ball. And I think this result was already known, rigorously proved only for special choices of A1 and A2, for example, if the diamond is a triangle. But I proved this now for general A1 and A2. And then the idea is to start with these equality cases and find affine transformations phi such that phi cross phi transposed to the -1, which is always in symplectomorphism, maps these equality cases into Lagrangian products of this form, and then one is done. Okay, and here one also sees why this method does not prove this result of Ostrova, Ramos, and so on. Because if we take here hexagons, then it is not possible to find here an affine transformation phi in order to map it onto a square. But for parallelograms, this is always the case. And concerning the proof of the answer to the last question, concerning this, we can say weaker Zoll property, this is just by analyzing the length minimizing billiard trajectories. And here we have again the triangle configuration, here the trapezoid configuration, here the parallelogram configurations. And one sees that if we start somewhere at the boundary where we are not in the vertices, then one has length minimizing billiard trajectories which are closed, also always closed. They minimize the length, and they have exactly 4 bouncing points, which translates for the underlying characteristics into that these characteristics are closed. They move on exactly 8 facets, and they minimize the action. And this can be done for all of this. And one also have the density of the Minkowski billiard trajectories for the sets on the left, as well as for the sets on the right. And this translates back into the density of the characteristics on the boundary of these Lagrangian products. Okay, and I will maybe stop here, and thank you for the attention.
Thank you very much. Questions?
Maybe I have a question. So my impression is that inequality between capacity billiard trajectory was proved by Arstein, Avidan, and Ostrover, at least in some situations. So how your results are related to that?
You mean this one, this first one?
Yeah.
Yeah, they proved this for K and T when they are strictly convex and smooth, especially if one has this bouncing rule over here. And I generalized this now for general convex sets. And this is, of course, important in order to analyze these polytopes, which appears as quality cases. But it is just a generalization of this method of Arstein, Avidan, and Ostrover, I think.
Oh, okay, great. I see. Thank you very much.
Yeah. So one only has to show that this conditions also hold if one replaces the smooth and strictly convex K and T's by polytopes.
Thank you.
And this is the reason for having here then, normal cones, which are more than one-dimensional.
I have a question. So you made a very interesting remark at the beginning, saying that the conjecture on equality of capacities would imply that the things with systolic ratio 1 are symplectomorphic to balls. But I'm having a little trouble understanding that because there are known examples in 4 dimensions of ellipsoids where there's an embedding of one, symplectic embedding of one into another, which fills up the whole volume, but they're not actually symplectomorphic.
Perhaps can you repeat the question? I didn't get the answer right.
Yeah, so you seem to be suggesting that if something has a Gromov width so that you can fill up its whole volume with a ball, then it's symplectomorphic to a ball. But there are examples of 4-dimensional ellipsoids where you can symplectically embed an open ellipsoid into another of the same volume, but they're not symplectomorphic.
So, and what is the thing which irritates you?
Well, and maybe I missed your argument, but you seem to be saying that if something has Gromov width so that you can fill its whole volume with the ball, then it has to be symplectomorphic to a ball. I'm missing how you prove that.
I'm not sure whether I understand the problem behind this question.
All right, maybe I'll email you about it and we can discuss it later.
In which dimension do you have this example?
4 dimensions. So like the McDuff's theorems on embedding symplectic ellipsoids in 4 dimensions.
On a different note, maybe you could comment on those other geometric problems that are related, that have those curious names, and are supposedly related.
Exactly, this was here. This relationship, this interpretation of Viterbo's conjecture as a couple of problems, and I also prepared a slide for this. So here I stated what it means to be a warm problem in general. So let us assume we have a collection of n-dimensional figures and a transitive group M of motions. And the task is to find the minimal convex target set, minimal in the sense of having least volume or surface volume or whatever, so that for each figure there's a motion such that this motion maps this figure into K, into the target set. And now we have different problems in geometry, for example, Moses' worm problem or Wetzel's problem, or Bellman's lost in a forest problem, which can be assigned as special versions of this general problem. For example, Moses' worm problem, which is find the convex set of least area that contains congruent copy of each arc in the plane of length 1 is the setting when F is a set of arcs in R2 of Euclidean length 1 with a group of motions is a group of congruence transformations, and the minimization is in the sense of minimal area of target sets. The Wetzel's problem is if we take the set of closed curves in R2 of Euclidean length alpha, M, the group of translations, and minimization in the sense of minimal volume of target sets. And now one can show that Viterbo's conjecture for these Lagrangian products can as well expressed within this general setting. If we take the set of closed curves in Rn of Minkowski length alpha, if we take the group of translations at the group of motions and minimization in the sense of minimal volume of the target sets, then one has expressed Viterbo's conjecture as such a geometry problem. And this Bellman's lost in a forest problem appears as equivalent formulation of Moses swarm problem. And one can say that also Viterbo's conjecture can be expressed as such a lost in a forest problem or escape problem. For example, I think we have 1 minute for this story. I will just read it out. So imagine we have 2 hikers walk in a forest, and one of them gets injured and is in need of medical attention. The unharmed hiker would like to make the emergency call. Although he has his cell phone with him, there's only reception outside the forest. He has a map of the forest, i.e. the shape of the forest and its dimension are known to him, and a compass to orient himself in terms of direction. Furthermore, he is able to measure the distance he has walked. However, he does not know exactly where in the forest he is. And then the question is, what is the best way to get out of the forest, put off the emergency call, and then get back to the injured hiker? And this is now a problem in, one can say, 2 dimensions. And for the Euclidean measurement, where this problem is equivalent to Viterbo's conjecture for these Lagrangian products K and T, where K stands here for the shape of the forest and T is responsible for the geometry of measuring the length. And I think these are some nice relations.
Cool, thanks. Maybe we have time for 1 more question.
Okay.
Okay. Although, I do want to ask another one.
Okay.
Do you suppose that maybe there's a billiard type approach that could tackle directly Euler's conjecture, maybe with a different billiard theory or something? Or
I have checked whether this is possible, but so far I haven't found any approach which differs from what I've done here. And I mean, in higher dimensions, it is more difficult to analyze the length minimizing billiard trajectories, because you can say that the dimension is proportional to the reflection points of the billiard trajectory, and this is, I think, very difficult, but in principle, perhaps possible to approach Mahler trajectory.
Okay, then maybe let's say thank our speaker again.